Hello, good morning everybody. So, today we have come to the fourth topic of our series of lectures. Okay, we have completed reaction rates, rate laws, effect of temperature on reaction rate. Then we have completed complex reactions. A great deal of discussion have been made, and next is theories of reaction rate. Okay, so we will start this topic from today. So, we will start with some elementary idea. Okay. So, the celebrated way of or the celebrated theory is the most elementary theory is the collision theory of gaseous reaction. So, we will start with elementary gas phase reaction, where the mode of reaction is via collision. Okay. So, all of us know that gas molecules, that is, if we confine some gas molecules in a container, then at a given temperature maybe we are confining some volume of or some mass of gas molecules. So, what will happen to them is that these molecules will move around, that is it will move to and fro within the container, and these molecules are making collision with the walls of the container, and this collision is responsible for the pressure that we experience, okay, gas pressure. Next is they are according to kinetic molecular theories, these gas molecules are thought to be hard spheres. Okay. So, the collisions are thought to be perfectly elastic in nature, and temperature of gas is a measure of mean random translational kinetic energy. So, and the thing is that when we consider a simple gas phase reaction like say A plus or AB, this is a molecule, and it reacts with say C D, this is another molecule, okay, giving rise to say A C plus say B D. It is a kind of exchange of portions, like this portion, these two portions are attached, and these two portions are attached as a result of this reaction. So, simplest way, and if this is a gas phase reaction, so simplest way to realize why this is happening is that if you consider that there is a collision that happened between these two. Okay. So, if there is no collision, then there is no chance that maybe this part is coming at a bonding distance to this part. So, this proximity, that is they should come, that is this part should come close to this part, and as a result of which this linkage is established. Okay. So, the collision may be regarded as the mode of mechanism that is responsible for this exchange process, exchange of parts of a molecule from one part on or from one molecule to another. Okay. So, to have a simplistic idea, we will consider that the molecules or atoms which are undergoing collision with each other, let us consider that these atoms or molecules are perfectly spherical in nature, maybe, although it is difficult to assume that a molecule, say maybe diatomic or triatomic molecule to be spherical, but for simplicity let us consider that it is a kind of hard sphere approximation, that a sphere is colliding with another sphere, and as a result of which we are getting the end product. So, basically collisions are the reason. Okay. So, let us look into this diagram, that we have got two molecules, one molecule is A, another molecule is B, and A is one sphere, B is another sphere. Okay. So, and say radius is like this much and the radius for B is this much. So, they will make a collision if this distance between the centers of A and B is exactly equal to the sum of their two individual radii, and under that condition they will make a collision. So, let us call that this distance to be DAB. Okay. So, when DAB is equal to their separation, that is separation means separation between their between the centers of two nuclei, then there will be a collision. Okay. Now, let us have a sphere like this. Say this is your A sphere, okay, and say there is another sphere, say this is your B sphere. Okay. So, if we draw a circle about the center of A with radius DAB, and then draw a cylinder of this sort, this cylinder. Okay. So, cylinder having radius DAB. Okay. So, this is DAB. So, what happens is that if any B molecule is having a position such that, that is in 3-dimensional space, if a B molecule is having a position such that its center is either within this cylinder, maybe here, or maybe just on this line, then we can call that there is a chance that this second molecule B will collide with your A molecule. So, that means all the molecules of B with their center within this cylinder will suffer the last collision with the molecule of A. Okay. That means, with time, if this molecule is moving, this A molecule is moving, this molecule is sweeping an area which is equal to pi DAB whole square, pi DAB square. So, this area is pi DAB square. Okay. So, this area, as if this molecule is moving, A molecule is moving, it is sweeping out, swept out area is pi DAB square. So, volume will be, if it is moving at a speed say of the order of, if this area is moving at a speed of say C average, then after time delta t, it will make a cylinder of volume pi DAB square into C average delta t. So, all the molecules, all the B molecules which are within this area, this volume, will suffer the last collision with this A. So, if we look into this figure, that the center of B molecule is within, and here the center of B molecule is outside. So, this is missed and this is hit. Hit means at some point of time this will make a collision with this one, but here there is no chance that this will make a collision with this. So, when there is no collision, that means no question of reaction, But when there is collision, of course there is an option for the reaction to take place. Okay. So if number density of a molecule is Ca, number density means number of molecules of A in unit volume. If it is Ca, then rate of change of concentration of A, rate of change of number density of A with time, with a negative sign, because it is reacting, this A is reacting, will have the collision rate, that is the total number of collisions between A and B, into a Boltzmann factor. Why there is a Boltzmann factor? Because not all the collisions are effective, okay? Or maybe this represents the number or the fraction of the total number of molecules having an energy, that is the threshold energy, either above or just exactly equal to the threshold energy. So this is the fraction of the total number of molecules having a minimum requisite amount of energy. That's why it is EC. Okay, so collision energy you can call that as. Okay, so minus dCA dt is equal to ZAB exponential minus EC by RT. Okay. Now you have to find out this ZAB, that is the collision rate between, when you consider the collision between A and B, total number of collisions per unit time. Okay, we have to find out. Okay. So collision rate, now we have to concentrate on to the collision rate of a single molecule. Single molecule means, suppose we have got a single molecule of A, which is, suppose by some means we have identified a single molecule which is moving around, okay? And suppose within the container there is only one molecule of B or rather A, and rest of the molecules are B. So we would like to know how many collisions are there, or how many collisions that this single molecule of A will make with all the molecules of B, okay? Means per unit time, that's why it is called collision rate. So let us call this ZA to B, which is nothing but equal to pi, that is DAB whole square, okay, into VAB average. Why VAB average? I am coming, and say this is your concentration of B, because we have got only one molecule of A and rest are B. So therefore, how many collisions will be will this single molecule of A will make will depend on the number density of B. If number density of B increases, so this left hand side will increase. So there is a direct proportionality. There is a direct proportionality between ZA to B and CB, okay? And of course it will also depend on this VAB. What is this VAB? VAB is the average velocity of AB. AB means, suppose there is a molecule, say this is A and say this is B, okay? And say this molecule is static, only these molecules are moving. So what is the relative velocity between A and B? It will be, since it is static, so it will be basically CB, or rather because we are using C as concentration, so let us call this as VB, okay, average velocity of B molecules. So in the same way, if this is also moving, then the average velocity will be the algebraic sum of this velocity and this velocity, okay. So relative velocity will increase if this is moving and that is also moving, because that will be an algebraic sum, okay. So that's why this VAB term has been introduced. If VAB is more, that means the area swept out by this circle of DAB in unit time will be more, as this average c, this it may be called as this average relative velocity between A and B, since it is more. So, the volume that it is making because of this movement of this this area pi dV square will be more. So, more number of molecules. So, this will cover more number of B molecules, or this will encounter more number of B molecules. Okay. So, that is why ZAB A to B, which is equal to pi RA RB square VAB average into CB is coming. Now, if the number density of A, now think that we are now putting more of A instead of only single A molecule, putting more than one molecules of A. So, in that case total collision rate per unit volume. Okay. Collision rate means number of collisions per unit time per unit volume, which is given in notation capital ZAB, which is your pi RA plus RB whole square, then of course this, because this is the effective volume within which if some molecule of B is coming, then it will make collision, times CB as as it was here, times CA, because we have now increased number of molecules of A from a single molecule of A to CA number density CA. Okay. And from Maxwell distribution of molecular velocities, so average velocity is 8 kT by pi mu. Pi mu means reduced mass of the system, because now we are considering A and B together, because they are moving relative to each other. That is why this reduced mass and center of mass concept has been introduced. Okay. So, that is why VAB is equal to 8 kT by pi mu. So, this VAB average is equal to square root of 8 kb, of course, this Boltzmann constant, by pi mu. Mu is the reduced mass, pi is the constant, and mu is MA MB by MA plus MB. So, mu is the reduced mass of the system, that is as if together say A and B, this mass and that mass together, there is this mu means as if this whole system is having a mass mu, and which is concentrated at the center of mass of the system of this system of masses. So, mu is equal to MA MB by MA plus MB. So, MA MB, these are the individual masses. Okay. So, therefore, ZAB is equal to pi RA RB square VAB average CACB. So, you can just plug in the expression for VAB, okay, and see what we are getting. So, capital ZAB, which will be equal to pi RA, that is pi DAB square, pi R square, times this is your length that it is covering in unit time, times CACB. Okay. So, this is the collision rate, that is total number of collisions that A and B molecules are making in unit time, in unit volume. Therefore, if you plug in this onto into the original expression, that is this expression, then we get this one, minus dCA dt is equal to pi RA plus RB square 8 kBT by mu. Okay. Then of course, here there will be a pi, because this pi has been somehow it is dropped in this. So, here we have to put pi over here, there should be 1 pi, there should be 1 pi. Okay. So, let me write it over here, because there is a little typo anyway. So, ZAB is equal to pi RA plus RB whole square 8 kB T by pi mu to the power half e to the power minus EC by RT CA CB. Okay. So, this is the I mean ZAB expression for ZAB. So, this ZAB into this will be giving you, left hand side will become now minus dCA dt if you multiply. So, this is your, this portion is your basically this one, this portion is your ZAB times e to the power minus EC by RT will furnish you minus dCA dt. Okay. So, this Ca is number density per unit volume. If we convert, if we want to convert this to concentration, that is moles per liter. Okay. So, that will give you, so Ca is equal to Avogadro number into Ca. In the same way, Cb is equal to La into Cb. Okay. So, in this way, if you plug in this information onto this expression, you will be getting in terms of concentration, that is moles per liter, it will be dCA dt with a minus sign is equal to La into pi Ra plus Rb whole square times 8 kBt by pi mu whole to the power half into Ca into Cb into exponential term. I am not just writing the exponential, it is basically your e to the power minus Ec by Rt. Okay. So, just make sure that you write here 1 pi and 1 pi over here. This is, there is a because of there is a typo graphical error. So, it was somehow it was dropped. Okay. So, what we are getting then, suppose we are writing, we are writing small ZAB like this, La Avogadro number pi Ra plus Rb whole square 8 kBt by pi mu whole to the power half. Okay. So, that will give you minus dCA, of course small c dt, which is equal to ZAB times e to the power minus Ec by Rt into Ca into Cb. So, these are small c, not caps. Okay. Therefore, if we compare a general rate equation, that minus dCA, that is concentration, this is in moles per liter, this Ca is in moles per liter, dCA dt is equal to small ZAB e to the power minus Ec by Rt. Okay. That means, this is your K into concentration A into concentration of B. So, basically this one is your K reaction rate constant. Okay. So, therefore, we can write Kr reaction rate is equal to small ZAB into e to the power minus Ec by Rt. Okay. And if we recall the Arrhenius expression, then your K is equal to A into e to the power minus Ea by Rt. So, now we have got a nice correlation or nice analogy between your Arrhenius expression, this is your Arrhenius, and this is based on your collision theory. So, please recall earlier lectures that I have told that this k is equal to a into e to the power minus E a by r t, where this exponential minus E a by r t, this term I called, or it is called as the exponential term, and this is called as the pre-exponential term. This is pre-exponential, this is exponential. Okay. So, this exponential term will increase with increase of temperature. Okay. This we already have discussed, and this pre-exponential term is also termed as your A, or the frequency factor. Frequency factor, that is, it has got some connection with frequency. Okay. Now, frequency factor, like so, Kr is equal to small z a b into exponential term, and your k from Arrhenius, it is a into exponential term. So, this one is your collision frequency, total number of collisions per unit time per unit volume, and this is your frequency factor. Okay. So, it has got a good correlation. So, therefore, there is a pre-exponential term, and here also pre-exponential term, but in this case collision theory, in collision theory, this is your purely a collision term. It may be a little bit complicated, but it has got a close correlation. Okay. Actually, it is found. So, therefore, A is, we can call that A is basically your ZAB, but it has been found from various instances, maybe after theoretical consideration, or maybe some experimental findings also tell us that this A is not exactly equal to ZAB for many cases, this small ZAB for many cases. Okay. So, it is found that A sometimes is less than your ZAB. So, collision theory may be predicting is predicting some number as to your rate constant of the reaction at a given temperature, but when you do the experiment, then it has been found that your pre-exponential term is lower than the predicted by the collision theory. Okay. So, in order to account for this apparent difference between this calculated ZAB and the experimentally obtained A new factor has been introduced this way. So, A is equal to A by ZAB is equal to P, where P is called the probability factor or maybe the steric factor also. Okay. That means, not all the collisions are effective in making a chemical transformation. So, probability wise P can be at most 1, but it may be less than 1. So, it is in between 0 to 1, it may be 0.5, 0.7, maybe 0.2, something like that. Okay. Now, what is this probability factor? That suppose we have got a molecule of, say, we have got these two molecules, okay, and suppose that we want to exchange this one with this one. So, in order to exchange this, what do we need? That maybe this will collide, this one will collide with this molecule, so that there is a direct contact between this molecule with that molecule. Okay. So, this collision may lead to a true exchange of this, like maybe after collision this cover goes to this cover goes to this one, and this cover goes over to here. Okay. Or maybe reverse situation, this collision, so this cover goes to here and the black goes over here. Okay. So, this may happen, but suppose So, this is not only the pose in which these two are colliding. Pose may be like this, maybe like this, or maybe in some other way. There is every possibility. That is why only those collisions which are with appropriate orientation, appropriately oriented molecules when undergo collision, that may lead to the effective formation of product. So, maybe if collision occurs like this, maybe this, nothing will happen. That is why in order to account for this apparent difference in calculated and the experimentally observed A factor, a new factor has been introduced to take into account of this apparent variation. So, therefore, it is called the probability factor. Sometimes it is also related to the steric factor, the factor which is arising out of again whether the system is having a specific orientation, specific geometry or not, or maybe say you have got say this molecule and maybe this molecule, they are colliding, but suppose if this molecule is a little bit complicated one and having some side chains which are covering this head. Okay. So, then this molecule, I mean this part of this molecule will not be able to come very close to this part. Therefore, the reaction will not take place. So, that means this part may be called as sterically crowded, sterically hindered, maybe commonly used organic organic terms. So, organic chemistry often use this term. Okay. So, this may account for the observed and calculated number differences. Now, we will talk on EC and EA. Now, K is equal to, as I told you, LA pi RA plus RB square, 8 kBT by pi it should be pi mu, pi is dropped somehow, I do not know why this happened anyway. So, this should not have dropped, maybe some software problem or something anyway. So, into e to the power minus EC by RT. Now, you take logarithm and then differentiate. Okay. You will be getting dln k dt is equal to half RT by EC divided by RT square. Okay. So, if you take logarithm and then ln, take ln and differentiate. So, therefore, you get activation energy. So, basically dln k dt is equal to EA by RT square. So, this is your EA. So, therefore, EA activation energy is equal to EC plus half RT. Okay. So, this half RT is coming as a result of maybe this term, which is having a square root of temperature dependence. So, K is having one term which is exponential dependence and there is a square root of T dependence. It is coming like this. So, basically EA and EC, they are separated by half RT term. Okay, half RT term. So, if temperature is not very high, then this term will be small. Therefore, for all practical purposes, we can write EA to be equal to EC. Okay. So, this is the relation between the EC and EA, that is energy, that is exponential term which is used in exponential energy term which is used in collision theory, and the term which is used in your regular Arrhenius expression. Now, for a single type of molecule, these are the corresponding expressions. You just can have a look at it. So, only one type of molecule. Okay. So, basically for one type of molecule, CAB or VAB should be replaced by VAA. Okay. And if it is moving at a speed of say VA, another is moving at a speed of VA like this. So, say this one is moving this way, another is moving this way. Okay. If they are moving in opposite direction, their velocity will be 2a. If they are moving in this direction, on same direction, their relative velocity will be 0. So, this number is varying from 0 to 2a. So, what is the average orientation? Average, that is, it may have this option or this other situation is this option. So, average angle, on an average you can call that they are at 90 degrees. So, this one will be root 2 CA or VA, V average. So, VAA is your root 2 VA for single type of molecule, and correspondingly you will be getting other expressions. Okay. So, for one type of molecule you will have this expression. So, let us have again this expression. We will start from Arrhenius expression and we will try to relate this Arrhenius expression with the expression for rate constant after collision theory, which is based on purely collision between molecules, and this is restricted to gas phase reaction, because in solution phase the situation is complicated, because one molecule is moving under the influence of viscous forces there in the solution phase. Okay. So, they are not very free to move around from here to other region of the solution. Okay. So, viscous drag is can complicate the situation. If we think of the viscous drag, that can complicate the situation. So, therefore, it is purely gas phase question. So, it is purely a gas phase description, that the collision model of reactant assumes that the rate constant is K, which is equal to P is the probability factor. This Z means collision rate per unit volume times exponential minus EA by RT. We have just replaced EC by EA because we have just shown that this EC is very close to EA unless the temperature is very high. Okay. So, and P is the steric factor, maybe not, which takes into account of the appropriate orientation or appropriate geometry of the molecule with which it is colliding, and not all the collisions are effective, only those collisions which are with appropriate orientation and having a requisite amount of energy. Okay. If the molecule does not have any requisite amount of energy, that is your activation energy, then it will not cross the barrier. So, reaction will not take place. Okay. So, so this exponential, as I told you that this your exponential term e to the power minus EA by RT is the fraction of collisions that have more than the, at least more than or equal to this requisite amount of energy. Okay. So, that is called your activation energy. Okay. So, if we consider this equation in terms of changing temperature, then so we should find out, okay, in terms of changing temperature, the steric factor clearly does not depend on temperature. Okay. And Z turns out to be only weakly dependent on temperature. Okay. How? You see, it is not exponentially dependent on temperature, this Z. Why? If you come to this expression ZAB, you see this has got a root over T dependence. Okay. So, it is not very strongly dependent situation. Had this been with an exponential dependence, then it would have been a different story, but it is not the case. So, the steric factor does not depend on temperature, and Z turns out to be only weakly dependent on temperature. The thing is that we are giving you an estimate that changing temperature from 500 to 600 Kelvin, that is by a factor by an amount of 100 Kelvin. Okay. So, that may change your Z by a factor of 10%, because it has got a root over T dependence. So, difference is about 100. So, root over 100, although not exactly, it goes as 100, will be about 10%. Okay, that it is basically 10. So, from 100 to we may have 110 or maybe 90. Okay, so it is nothing but a 10% change if you move from 500 to 600. Okay. And steric factor, suppose we have got say a hydrolysis reaction, say tertiary butyl chloride, say like this one. Okay, we have got Cl, okay, and here it is methyl group, and you have got OH minus. Okay. So, it will attack from back side. Say this is a celebrated example of hydrolysis of alkyl halide. Okay. So, if had this been occurring via SN2 mechanism, substitution nucleophilic bimolecular, then you will be seeing that it has got a huge this methyl, these are bulky groups. So, this side of carbon is this side of carbon is more or less blocked. So, this OH will not be able to approach from this side to displace this one. So, this displacement by this backside attack is probably impossible. So, that means this particular this reaction will not take place in this particular way. That means, this mechanism is not an acceptable mechanism for this situation. So, that means your steric factor says that this reaction will not take place in this mode. Okay. But maybe say in other case, say you have got methyl chloride CH3Cl, in place of 3 methyl group you have got 3 hydrogens. So, what will happen? This OH will easily attack your carbon from backside, and this displacement will take place. Okay. This displacement will take place and thereby producing your requisite alcohol in this mode, in this mechanism. So, this backside attack for this case is not possible, but the backside attack is possible for this case. Okay. So, this proper orientation factor and also the steric factor plays these two play a very important role in determining whether some reaction will take place with ease or not. That means, your kinetic theory of gas predicts that maybe this collision between your maybe, although it is a solution phase reaction, I am just giving you the idea that your collision theory predicts that if there is a collision between this unit with that unit, then like this, then reaction will take place. But the thing is that if there is some screening effect, that this part cannot come very close to this part, okay, maybe there is a shielding effect, therefore, this part may not be able to come very close. So, this part may not be able to form a chemical linkage with this part, so that some required reaction may take place. Okay. So, that is why steric factor is so important, such an important thing that we should take into account, and this is just to match, this steric factor has been introduced in this expression just to match your experimental result with the theoretically predicted after your collision theory. Okay. So, this is just to match your experimental result with your theoretical result. Although it is very successful in many gas phase reaction, this theory predicts reaction rate quite close to your experimentally observed rate constant. Okay. So, in this way we can say that this is the first successful attempt towards the understanding of reaction rate, why this reaction is taking place, why this reaction rate increases with increase of temperature. So like if we try to apply Boltzmann distribution, say this is your lower state, say this is your upper state, and suppose if these molecules, if your molecules do not come to this upper state, it will not be able to proceed for reaction. So, that means you need to put your molecules from here to here by some means, maybe by heating, that it will acquire energy and this molecule will jump from here to here. So, that now these molecules are ready to react. Okay. So, Boltzmann distribution says that the more the energy separation between L and U, the more is the temperature required to transfer your lower state molecules to upper state molecules. That is, high temperature will tend to increase the reaction rate. Low temperature may not be able to do any effect onto the change of reaction rate with temperature. Okay. So, that means you are increasing temperature, means you are increasing this factor, exponential factor. This exponential factor, that is exponential minus E by RT, this factor is the factor, it is your partition factor, that how many molecules will be partitioned between these two levels when your energy gap is given, whether more molecules will be here or more molecules will be here. Since it is higher in energy, so natural tendency is that more molecules will be here, but as you increase the temperature, some of them will jump from here to here, acquiring some requisite amount of energy, and when these molecules are here, then they are ready to react. But again there is a question, becoming ready does not necessarily mean that it will lead to some effective reaction. That means these are ready although, but they may collide, they may not collide with a requisite orientation. Okay, if they do not collide with requisite orientation, then reaction will have very least probability to proceed further. So, that collision will be ineffective. So, some of the collisions are effective, some of the collisions are ineffective. So, in order to match these two with respect to the total reaction yield, we have to introduce this probability factor. Okay. So, this is your Boltzmann factor, that factor if you increase, so more molecules will jump from here, so more will tend to react. Okay. So, it is a purely collision model, and it is purely a classical description that takes into account that these gas phase reactions do occur only by collision, they will collide and they will react. If no collision is there, then no reaction. That means if you rarefy, I mean if you put some inert gas into reaction mixture, then these molecules will, I mean reacting molecules will get separated from each other. So, separated from each other means their probability of collision, forget about this collision with proper geometry or proper orientation, just their probability of collision will be reduced, So, probability of collision reduced means the reaction rate decreases. So, why this is happening? Because your rate constant contains two terms, two concentration terms, I mean number density terms. So, number density terms reduce, therefore, reaction rate decreases because collision is also reduced. Okay. So, that has got a very important consequence, and this is the first possible way to rationalize reaction rates and why this is happening, how how temperature can affect your reaction rate. So, that is a very important question, and that we have been able to give some justification. Okay. In our next slide, we are just trying to understand one point, that these two graphs, you see that it's a Maxwell distribution of molecular velocity. So, it's a number of molecules, and this is a this way kinetic energy increasing, although this should be plotted this is your number of molecules, and this is your number of number of molecules, and this is your dNc by n versus n. Okay. Or so what is happening, dNc, so you are plotting number of molecules as a function of maybe energy, or maybe as a function of C also, not n, as a function of C. So, it is a plot of number density versus it is a plot of number density, or dNc by n, and your C, this way it is your C. So, you see that it starts like this, and then it is an exponential decaying function. So, if you increase the temperature, so you see higher temperature, the red graph, it is flattened, and your top, this region is shifted with respect to this top. So, this is your most probable velocity, that is the probability of having this velocity is maximum. It is basically a probability function. So, if you increase the temperature, it is flattened, but suppose if this is your line corresponding to energy of activation. Actually, this plot is the plot of dNc versus C. C means molecular speed, but this Ke with an arrow means that this way Ke is increasing, this way Ke is increasing. Actually, this is a dNc by n versus dNc, number of molecules with an energy between C and C, with a velocity between C and C plus dC. This is your dNc, and this is your C. Okay, this is your C. So, if you see that this is your this line is corresponding to activation energy. So, this is a graph for lower T, and this is a graph for higher T. So, you see that for lower T, your number of molecules with energy Ea or more is this much, and if you increase the temperature, this is the total number of molecules with energy equal or more than Ea is this much. So, you see number of molecules increases as you increase the temperature from T1 to T2. So, that means you have got more number density with requisite amount of energy, at least requisite amount of energy. So, naturally what will happen, you have got more fraction of molecules which are capable for doing some chemical transformation. Therefore, increase of temperature leads to an increase in rate, that we can successfully explain, and that is a successful and qualitative explanation. In some cases, it has been found that your calculated one based on this theory, that is your collision theory, gives you the right estimate for many reactions. Okay. Now, let us sum up. So, in this lecture, what we have learned. Okay. So, this is the first attempt to explain your theoretical explanation of your reaction rate, why this reaction is taking place, and we have tried to explain, and we have tried to understand that collision for a homogeneous gas phase reaction, collision is the cause of reaction to take place. So, reaction happens as a result of collision. Okay. So, more collision, more reaction. Okay. And somehow if you can increase the number of molecules with some requisite amount of energy, that is your exponential factor, then you can in principle increase the rate. And also at a given temperature, this depends on this rate constant will depend on not only on this exponential factor, that is your partition factor, but also on the factor, that is your collision factor, that is your frequency factor, that is how many number of molecules, how many collisions are there in unit time, in unit volume, that is frequency per unit volume. If it increases, then reaction rate increases. Okay. And also in order to account for the fact that in some cases the predicted number for K has been found to be more than the than your experimentally observed number. So in order to cope with this one, so we have introduced a factor which is called your steric factor, which takes into account that not all the collisions are effective, that is collisions means all the collisions do not take place with the requisite geometry. Okay. So in this way we try to have an understanding of this theory of reaction rates based on collision theory. It is a purely collisional model and purely based on kinetic theory, and the collisions are thought to be elastic in nature. Okay. So in our next lecture we will talk more on this theories of reaction rate, and we will try to move on to transition state theory. Okay. So and we will have more discussions, more example to have a complete understanding of theory of reaction rates, maybe in solution phase, maybe in gas phase. So till then, have nice time. Bye.